Today we will start to discuss some outbreaking the encryption about encryption scheme. Okay. So first about the cipher text only attack. The truth has a cipher text she can analyze. Two approaches: the brute force search all through all the key, and the other approach is statistical analysis. The other one is the non-plain text attack. The truth has a plain text and corresponding the cipher text. For example, is in the monoalphabetic cipher, and the truth determines the pairings for the like the alias or BO. So you will choose the plain text. The truth can get a cipher text for the choosing the plain text. For example, you can see like the symmetric-key cryptographic. So here, the plain text here. So encryption algorithm using the case, the encrypt algorithm. The cipher text right now is case over message of M. So this is a plain text of M, and the cipher text here is encryption. After encryption, the cipher text, the case over M, then decryption algorithm using the same key. That's why we talk about the symmetric-key cryptographic. So use the same key case and compare to the plain text. So we talk about the symmetric-key crypto, which means Bob and Alice shares the same key. That's why the key is K. So we talk about the symmetric. For example, K is known in the substitution pattern in monoalphabetic substitution cipher. So here is the question: how do Bob and Alice agree the key value, right? Because it's a key to share. So how do Bob and Alice agree the two key the value? We can see. Some is a simple encryption scheme here. Substitution the cipher. The substitution one thing for another. More alphabetic cipher. Substitute one later for the other. For example, in plain text here. So you can see it's like A, B, C, D to the Z, S, Y, Z. But we can encode the other cipher text. Like A change to M, and D change to Q. So B change to N, C change to B. So plain text is a message. You can see the Bob, I love you, Alice. So for example, you can see B, right? Here, plain text B. We encode the plain text to the cipher text. B change to N. So BOB is a N. O is which means K. So BOB which means NKN. So we need a table mapping. So the Bob, I love you, Alice. So change to NKN dot, like the following character. The encryption key here is mapping from the set of the 26 letters to set of the 26 letters. It's like this mapping. Some sophisticated encryption approach, for example, like substitution, the cipher M1, M2 is MN. The cycling pattern, for example, N equal 4, then M1, M3, M4, then is to the cycling. Then M4 change to the M3, M2. It's like cycling. The M1, M3, M4, M3, M2 is like a cycling pattern. For each of the plain text is simple, using the substitution pattern in the cycling patterns. So dog from the M1, right? second pattern here. So M3 is O, right? The G is M4. So it's like this, the second pattern. For each of the plain text symbol with the subscription substitution. So we can see the encycling pattern. So D from M1, the O from M3, and the G from M4. Yeah, it's like this rule. And the encryption key, the N, this N, substitution, ciphering, N substitution the cipher. So ciphering pattern, so N, which means substitution cipher, and the ciphering pattern. So key need not to be just an N-bit pattern. The other symmetric key crypto is DES. DES actually is a Data Encryption Standard. The US Encryption Standard in 1993 on NIST. Actually, is a FIPS 56-bit symmetric key and the 64-bit plain text input. So block ciphering with the ciphering blockers training. So how secure is the DES? The secure, how secure level, right? How can we evaluate the DES? Actually, the DES charge is 56-bit key encrypted, a fast decrypted, the brute force in less than 1 day. So no good analytic actor. And making DES the secure, the 3DS we can using the 3DS include 3 times with 3 different keys. So it's 3 times. The other is very popular is about the AES. AES is called Advanced Encryption Standard. It's a symmetric key NIST standard. It's released in 2001. Replaced the DES. So processing data actually is 128-bit blocks. So it's 128 and 192 and 256-bit key. So brute force encryption try each key, taking 1 second on DS. Actually, we need to text 149 trillion years for AES. So which means AES is very secure. So secure level AES is better than DS. Also, public key cryptographic actually is need symmetric key crypto. So require the sender receiver no share important and share secure key. So question, how to agree the key in first place, particularly when we never meet, right? So public key the crypto is radically the different approach. Actually, is a different element in ISA 78. The sender receiver do not share the secret key. In this condition, so public key actually the public encryption key no to all, right? It should be the public key cryptography. So private key, private decryption key known only to receiver. So you can see the public key cryptography, the plain text and message M, the encryption algorithm as to send the bubble, the public key, the KB plus bubble public key here, the share to the Alice. They use this bubble public key from the share to the bubble and encrypt the plain text, the message. So the ciphertext using the bulb key, the KB plus of the M using the bulb key from Alice and the plain text and go to the encryption algorithm using the bulb key and send to the bulb. The bulb decryption the algorithm using the bulb K minus private key. Because it's a key pair, right? It's public key bulb and the KB plus, and the bulb key is minus. Actually, it's key pair, public key and the private key. And when we use the decryption the algorithm using the bulb private key, then we can use the bulb private key and the bulb public key and the message to plan the text to M. So very important. In the initial, we need to send to the bulb private key to the Alice. And when we receive the bulb using the private key over the bulb, and the plan change to the decryption algorithm and the plain text, the message. So it's a key pair of bulb and recover the message. So it's very wonderful standard mechanism. It's PUB key cryptography revolution in the 2000 years old. Previous all these symmetric-key cryptography. So it's a very similar idea emerged at roughly same time, independent in UK and the US classifier. So it's very useful the public key cryptography revolution. So we can actually follow the public key encryption algorithm requirement. Because we need a public key, right? The plus, bulb public key plus the function. And the bulb private key function, such like this. We need to agree the bulb private key and apply to bulb private key and to the message plain text and come back to the message. And it's first equation about this requirement. And when we give the public key, the key bulb key of the pass, it should be the impossible to complicate the private key bulb private key minus. So we can, even with given the public key, we cannot calculate the public key to get the private key. So that's why we talk about the state here. It should be impossible. The very important is impossible to compute the private key of the bulb of private key. So I say, which means Rijndael and the Shamir Ellison algorithm. So it's we requested the module arithmetic. We can see the sum equation here, the S mod n. What does this mean? The S mod n is a remainder with S mod n is a remainder of X. It's called when divided by n. So X divided by n, the remainder. We want to get this remainder. It's like a classify X mod n the classify. Okay. So we can see the facts, the A mod n and plus B mod n, the equation, the mod n. Then we can say the A mod n plus B mod n is, we can use the operator here, A plus B and mod n. And the sum equal here, A mod n here, minus the B mod n here, then mod n. So we can also A minus B mod n. The other remainder calculate here, A mod n, the remainder, and B mod n, the remainder. Then mod n. Then we can use the A plus A multiple B and mod n. So thus we can apply here A mod n D and mod n, then equal to A apply D mod n. So for example, you can see if the x is 14 and n is 10 and then d is 2, so x mod n d, and you can see it's 14, right? 14 and 2 is 196. 196, the 196 and n is 4 by 2. So mod 10 then is equal to 6. So if xd here also mod 10, here 4 square mod 10 is 6. And the 196 mod 10 is also 6. So we can see is D is square here, the same square. X is 14, x14 square, and is here n is 10, the mod n mod here, so it's the same result. So I say we can get a getting ready. The match just a bit of pattern, and the big pattern can be uniquely represented by an integral number. So big pattern actually is uniquely, and uniquely represented by the integration number. Thus, the encrypting is a message equivalent to the encrypting a number. So encrypting a message is equal to the encrypting a main number to number. For example, like M, like this message encrypting a number. The message is uniquely represented by the decimal, the number here, change to here, 145. To include the n, we include the corresponding number, which giving the new number. So the n, the equivalent this number here, we include the corresponding number. So given the new number. That's the cipher text. So ISA are encrypting the public and private key pair. They choose the two large priming the number P and Q, the priming number, the large priming number. Actually, it's 1024 bits each. So n is a priming number multiple. Priming number multiple is a P multiple Q, and the Z equal to the P minus 1, and the multiple the Q minus 1. So these are RSA rulers. So we choose the E. Actually, E with the E less than E less than no common factor, and with Z. And Z are the relative priming. So we choose the D. D such as is the D is also -1. D -1. It actually is exactly divisible by the Z. So in other words, ED mod Z equal 1. And we can say the public key actually is N and E, and compared to the public key of the K positive. And private key actually is N and the D of the function, the private key. And we choose the E is a low common factor, the public key, and the D is exactly divisible by Z, and here is the D, and we can use the N and D, the key function of the private key, to the KB minus the private key, KB of minus, and the public key, KB of plus. So you can see the either encryption, the decryption, for example, is the N and E were given N and E, and the N of D, a public key and the private key as a computing above is to encrypt the message M. M actually is less than computing. The C equal M, the E and mod N, and decrypt receive the bit pattern, the C computing, the M equals C D mod N. So it's the public key encryption here is based on the N and the E to get the message here is to get C. The message is come back decryption, decryption receiver the bit pattern message here, and the C will get C here and apply the D and the mod N, also mod N here. So magic happen. The message here N, right? The M E, the M E, and mod the N, and the D, and the totally actually is C. You can see here the ME mod N here actually is C, and the C, the D mod N actually is M. So it's very magical happen. So we compare to the message the M. So I say for example, the Bob choose the P equal 5, the Q choose the 7. So N the premium number is N is 35 and the D is 24. So E actually is E and the D relative prime. So E is 5 and the D is 29. So ED minus Y exactly divisible by the D. So we encrypting the bit message, for example, like encrypt a bit pattern here like this one. So you can see the M, the message M is 12. So M the E is here 5. So it's in this number. And the C is NE mod N. So it's 17. So 17 we get a C, right? That is now the encryptor is a solution here. We get a C, the message from the message to the C. But we want the decrypt the C. So right now the C is 17, and C the D is a huge number. Wow, it's big, huge number. But C mod n, CD mod n is 12. So 12 actually is, what does this mean? It's message, the 12. So it's very magic solution, magic from the encryptor and the decryptor. We encrypted the 12, and based on this RSA example, we decrypted the 12 to get this message. So it's a wonderful, wonderful magic solution on RSA using this mechanism, the encrypting the 8-bit message. Right? It's M, actually is totally the same. So how does the RSA work? Must show the C, the D mod n is M. And where the C, the ME mod n. The factor actually for the any X and Y, SY mod n. The S actually is applied Y mod D and mod n. The number of n actually is a P multiple Q, and the Z actually is a P minus 1 multiple Q minus 1. So thus we can see CD mod n. Actually, C, what does this mean? C here is ME mod n. So here, apply here. The D mod n. So when we get the D apply here, so D come join here, ED, the MED mod n. So M, the ED mod n come back to here, then mod n. So we can get the mod 1, mod n to get M. So it's very good result. So SY, the mod n, actually is S mod Z, and mod n is here. So based on this understand, you can totally understand. I say another important property. The following property will be very useful later because we send the public key and we decrypt using the private key. So private key, the decrypted message, and the private key decrypted message will get M. So private key, if we apply the private key first, then using the public key, the answer is the same. They get the same message. So we use the public key first, allowed by the private key. So we can get the same result. Result actually is the same. Use the private key first, allow the public key. It's a very interesting result. So it's very, very interesting result here.